So it will be moving forward with the topic process management. We'll be seeing various things like process life cycle, how process moves from one state to another. So let's begin. Now, the definition, program and the execution is simply called process. So whenever a program, what do you mean by program? Static code, you can say, is program, and a program under execution is called process. Now, some few important points. The program should reside in main memory. Main memory, I mean RAM. Now, the occupied the CPU to execute the instruction. Active and dynamic. Active means it should be in the CPU, executing in the CPU, and dynamic means it takes some input and output. Yeah, I'm talking about process. These are some important things about process. Whereas program is static and passive. That is, it does not take input and output. And active and static. So attributes of process. There are some attributes of the process. It's better if you learn all of them because sometimes they ask an exam. Now we'll be seeing each of them one by one. So first is process ID, process state, priority, program counter, general purpose register, list of open files, list of open devices, protection information, and protection information. All of these can vary from system to system, but some things remain constant. Like process ID, it is unique identification number. Each process will have its own unique identification number. It will never happen that two processes will be having the same process ID. Never. Now, process state, in which state the process is residing, whether it's execution in the execution state, or it's suspended, or in the block state, or it is in the ready queue. So that will be known by the process state. Moving forward is the priority. Now, whenever the process is created, it can be assigned some priority based on the CPU scheduling algorithms, and we'll be seeing as we move forward. Program counter. Now, suppose I have this program with instruction I1, I2, I3, I4, I5 with addresses 10, 20, 30, 40, 50. Now, as you all know that CPU executes in round robin scheduling kind of way. So let's suppose when my process starts execution when my process start executing these sequential statement, it started executing I1, I2, then the time quantum expired, and after this got preempted here. And as you know, preemption is a temporary stop. When it will come back, how it will know okay, I have to execute the I3 statement. Now that will be known by the program counter, because program counter stores the address of the next instruction to be executed. So when this process will be preempted at I2, after completing I2, the PC will store the address to be 30. And when the program resumes back, this the when the program resumes back, CPU will know yes, I have to start executing from the program counter which is storing the value 30. So I3 will start executing, and the execution will continue. And a very important statement I have used here is that preemption is a temporary stop. We'll see why it is important as we move forward, and we'll continue to semaphores and other parts. So let's move forward. General purpose register, to store these information like local variables when the program is under execution. Some general purpose registers are used. Now, context of the process. What do you mean? What do I mean by the context of the process? Is attributes of the process. We have seen these attributes of the process, that is process ID, process state, priority, program counter, general purpose register, list of open file. I'll show you attributes of the process. It is also called as context of the process. Okay, it is also called as context of process and will be stored in the process control block. It is also known as process control block, and every process will have their own PCB. You'll be thinking like it will be a very big overhead for the system. Yes, it is overhead for the system, but it is necessary to maintain his hassle free execution, because many things are required when process get preempted. it Program counter is needed when process needs to be executed fast, or it is of higher priority is required, and protection information, etc. Now let's see the process state diagram. Before that, process can have various states. As I told you, process state attribute has process state, we had process state attribute, right? Process state. Now let's see what are the various states that it can be. New process is just created. Ready, it is in the ready queue running, it is with the CPU running. Wait or block, it is doing input output, or it is in the block state. termination, it is completed. Suspended ready and suspended wait, will see what these are. Now operations that can be performed in the process are creation, scheduling, dispatching, executing. Now let's just come to the process state diagram and we'll see how this works. But before that, I told you in the previous video that multitasking is an extension of multi-programming. I repeat, multitasking is an extension of multi-programming. What does that mean? That suppose the bigger circle is multi-programming and the smaller circle is multitasking. I can say multitasking is a specific domain of multi-programming. Why did I tell you so? Because multi-programming is of two type: non-preemptive and preemptive. Non-preemptive means no force is applied when the process enters CPU. It is up to the process when it will go out, and then we can schedule another process. That is multi-programming. And in preemptive, I say कि go process go process one into the CPU, and after 2 seconds I'll preempt you. That is according to time sharing, according based on some time that you'll go to you go to the CPU for 2 seconds, and if you complete before that, good and fine. But if you take more than that, I'll preempt you, I'll stop you, and will schedule another process. So that is multi-programming. And multitasking is a type of preemptive multi-programming. That's why I said multitasking is an extension of multi-programming. Now coming back to the diagram, yeah, this process state diagram, it might look very hideous, but as you understand what is going on, things will become very easy in life. Let's see whether do I have to cover anything else for you to understand this better. I don't think so. Let's see. Now process is of two types: CPU bound process, input output bound process. CPU bound process is the process which take more of the CPU time is called CPU bound, as the name itself indicate. And input output bound process are those which require more time, more amount of input output time. Now I guess I should continue. Like, let's see the diagram. Now the process first is created from the new state, it goes to ready state. I have written something as LTS, we'll see what it is. But suppose the process moves from new to ready state, it is into the ready queue. Here many process can reside at the same time. Many process, just keep notes because I will be telling the important points, repeating important points. Now process in the ready state, according to the some algorithm, CPU scheduling algorithm, it will be dispatched to the running state. Here in the running state, if the process is completed, it will go to the termination or completion state and will be destroyed or whatever happens. Now if the process requires an input output, so it will go into the wait or block state. And from the wait or block state, when it completes the input output stuff, it will not directly go into the running state. Why? Because another process might have been dispatched to the running state when the process P1 was going to the wait state for input output. Let's say like process P1 is first into the running state, and process P1 requires an input output, so it goes into the block state. In that meantime, when it was scheduled to the wait or block state, another process P2 is scheduled to the running state. Now process P2 is here, P1 is here. Now P1 completes input outputs cannot be directly assigned to running state because process P2 is directly here, is already here. So it will first go to ready state, and then ready from ready state it will be dispatched to running state. Now what are these states here? Suspended ready, suspended wait. Now in an ideal world, resources are infinite, but this is not ideal world, right? We have limited resources, right? So in the ready state, when the ready queue gets full or more number of process gets here, it will be difficult to manage, and many process cannot be in the ready queue simultaneously, so some of them gets suspended and they go into suspended ready. Similarly, in the waiting queue, some of the process get suspended and they go into suspended wait. Now these two states, suspended wait or suspended block, and suspended ready, they reside in the secondary memory because RAM is already getting full because of the ready queue, or because of the wait block queue. So it will be wise for them to wait in the secondary memory. Excuse me. As you can say, when the process is in suspended ready, then it is residing in the backing store. Backing store is just a technical term for the secondary memory. Now, who does all that work that I have told you, like from new to ready, sending from ready to run, sending from waiting to suspended waiting? Now, these are some processes known. Yeah, these are processes that does this work. These are LTS, MTS, and your STS. I have written here, I hope it's visible. Long term scheduler, short term scheduler, mid term scheduler. I hope this is clear. Once you'll read the theory by your own, it'll get crystal clear. I'll be sharing the notes. So let's see what are these LTS, MTS, three schedulers of OS. But before that, let's see degree of multiprogramming. What do you mean by degree of multiprogramming? uh, Whenever I'll say multiprogramming, I'll be saying number of processes present in the main memory at that point of time is called as degree of multiprogramming. If I say 10 is the degree of multiprogramming, means 10 processes are lying into the main memory. That should come to your mind when I say 10 is the degree of multiprogramming. Or if I ask you what is the degree of multiprogramming, you'll be telling the number of processes at that point of time in the main memory. Now, context switch. This definition is important, a little important, because it can be asked in the gate exam also by simply giving the options, because it has been repeated previously. So context switching is nothing but saving the context of one process and loading the context of another is called as context switching. And now, what do you mean by context? I hope you remember that context is the attributes of the process. Now, whenever you want to start another process, or when start another process and stop one of the process, context switching takes place, because you have to save the context of the previous context of the running process, right? Whenever you're stopping that process, so in that, context switching takes place, because you have to update the PC counter, you have to update whatever the registers are, general purpose registers. So context switching is simply saving the context of one process and loading the context of another. Now, if the context of the process, the attributes of the process are more, then context switching will take more time, which is really undesirable. It is very bad if you're taking very long context switching time, because it is simply overhead, right? You're not starting any process in between, you're just saving the context of one process and loading the context of another. So it is very big overheat for the for the system, and it is not advisable that you have very big context, and it will take more time for context switching. Now let's go forward. If there is one process, then it will still consider. Now, I have written that saving the context of one process and loading the context of another process. It might be possible that one process and another process might be the same process, because in robin scheduling, what happens is, if I have only one process that requires 10 milliseconds and I have time quantum of 2 milliseconds, then I'll be scheduling P1, that process, for to the CPU for 2 milliseconds, then I'll be preempting it, stopping it after 2 milliseconds, and then since I have P1 only, I'll be scheduling it again to the CPU, right? Stopping it, again scheduling it, stopping it, again scheduling it. In that, context switch does takes place. It will also be called as context switch, right? Now, I have three schedulers in OS, as here in this diagram I was talking about: LTS, STS, MTS. So let's talk about the schedulers right now. There are three types of scheduler: long term scheduler or job scheduler, short term scheduler or CPU scheduler, mid term scheduler or your medium term scheduler. Now, long term scheduler, where does it work? It works from bringing the process from new to the ready state. Yes, from new to the ready state, long term scheduler is used. This diagram is really important, and if you draw it right like this, you'll be getting full marks, because teachers are not usually taking the theory part, they will only be seeing the diagram. So now let's move forward. Short term scheduler, it is responsible for selecting one of the process in the ready state for scheduling onto the CPU. Now, I have shown you in the ready queue many process can reside, right? Remember, ready queue many process can reside, but in the running state only one process will be running at a single instance of time. Okay, so from ready state to the running state, who assigns it? It's the work of the STS. The process selection will be done by the STS. Now midterm scheduler, it does its job is also called as swapping. Why it is called swapping? Let's move to the diagram only. Here here it is, when the waiting block is getting full, the process are getting suspended, and they are getting stored in the suspended block or suspended wait. Who does that? MTS does that. And resuming also is done by the MTS. Suspending, resuming, suspending, resuming. It is also seen as swapping. You are swapping the process. First it's going to suspended block and then it's coming back to the waiting block. Now moving forward, dispatcher. What is dispatcher? Now, important thing. Short-term scheduler. I said you short-term scheduler selects the process from ready to running. It does not dispatches it. Who dispatches it? The dispatcher does the work, starting the process. Now, dispatcher, this definition is a little bit important because it is responsible for loading the selected job onto the CPU. It is also responsible for performing context switch. Now, is LTS important? Yes, LTS is very important. It might seem that it's just creating process from new to ready state, but it does control the degree of multi-programming. How it control the degree of multi-programming? Because a good proportion of CPU bound input output bound processes are required to be selected by the LTS. Why? Because if I say I make 10 processes and all of them are requiring CPU time, all our CPU bound process. So the utilization might go down, because throughput might go down, because all the one process will be first assigned to CPU, all the processes will be waiting for the CPU time, then second will be assigned, the remaining will be waiting for the CPU. Now let's see the scenario where five processes are requiring input output and five are requiring CPU bound. Now first goes and it required the input output, simply goes into the input output state, or the state, or suspended state. In the meantime, the second process is assigned to the CPU and it requires CPU bound. So in the time the CPU bound process P2 is getting completed, the pwin is executing its input output processes, so throughput is simply getting increased. So it does control the degree of multi-programming, and the good selection of the CPU bound and input output bound are processes are required to be selected by the LTS, long term scheduler. Now, what is this wait to termination? Like, my process requires to do some input output, and just input output, and then require it's and does not require anything else. So you might be thinking that why can the process go from wait to direct termination, right? This is not possible, because after going from wait, because termination is process getting terminated, right? So after doing the input output processes, the many context savings things, updating the register, updating the program counter, etc., are also done. So the process is first assigned to ready, it goes into running, performs little of the computation, and then it goes to termination state. It cannot go directly. A little bit theoretical thing, but it's okay. Now burst time, arrival time, we'll be starting next CPU scheduling, and I'll be telling you there only this burst time, etc. So that's it for the today's class. Thank you guys. Please like and subscribe.